Kayla, and this is my group, and we're presenting 3-person IVF and mitochondrial diseases. So we want to start off our presentation by having each of you imagine that you and your significant other are expecting your very first child. So after the arduous process of labor, you give birth to a seemingly healthy baby, but only 2 hours later, doctors come to you and tell you that your baby has passed away due to lactic acidosis. This was the horrific reality for Sharon Bernardi. Sharon Bernardi has Lee's disease. It's a mitochondrial disease that actually was passed down to all 7 of her children, 6 of the 7 who actually died before the age of 2. Apart from them, Edward lasted actually until age 21, but he had a very difficult life. He had up to 6 hours of leg cramping. He had neurological defects, cardiac defects, and generally had a pretty low quality of life. Now we have a happier story of Alana Saarinen. Alana Saarinen is just like any other 13-year-old girl, but she was actually susceptible to very similar cytoplasmic defects as Edward. So the difference here is that she was actually part of a study done in the late 1990s that actually produced 17 3-person IVF babies for the very first time. So she's actually among about 40 people in the world that have 3 genetic parents. But unfortunately, the FDA actually banned these procedures starting in 2002, but the UK brought them back this year. So why are these diseases so significant? I think everyone in this room knows how important mitochondria are. And we've learned about some of the diseases that can develop and how debilitating they can be. In terms of prevalence, about 1 in 250 people actually carry these cytoplasmic mutations in their mitochondrial genome that can actually give you these horrible symptoms that are listed above. But how do we fix this? So there's about 500,000 mitochondria per egg cell. It seems almost impossible that we go in and fix each one of these little genomes. But it's possible through 3-person IVF, which is essentially a way for parents to use specialized in vitro fertilization to actually have a third party donate their healthy mitochondrial genome from a separate egg. So they have to be pretty clever with this. One of the ways they do it, the most common way, is pronuclear transfer. So pronuclear transfer is essentially when you take the sick egg above and fertilize it with the same father's sperm that you fertilized the donor egg. So just remember, the purple cytoplasm is the sick cytoplasm with the bad mitochondria. You remove both nuclei and put your intended parent's nuclear genetic material into the healthy egg cell from the donor. So then you have a perfectly healthy embryo. The second way they do this is a maternal spindle transfer, or MST. And the biggest difference to remember here between this and PNT is that the genetic material is transferred before the actual fertilization. So the same kind of thing happens where they remove the mother's nucleus and they implant the intended parent's nucleus into the new egg cell with the good cytoplasm, and then they actually fertilize the eggs. That's kind of the biggest difference between the two. All right, are there complications for these selfless donors? There's actually a pretty low chance of ovarian overstimulation, disorders that develop after the procedure. And there's a relatively low chance of experiencing post-retrieval complications. But there was actually clinical trials that started in 2001 to study the longer-term effects of mitochondrial donation in general. So we're still getting results back from that. But the UK deemed this year as not unsafe. So has there been pushback? Of course there has been. Embryonic research in general always has pushback. Pronuclear transfer is kind of the utmost concern because they do destroy an egg that was fertilized. That bothers some people. Also, some religious groups have pushed back, and a Catholic bioethicist actually described these proposals as extraordinarily reckless with the lives and health of future generations. So clearly not everyone's in support of this. But there also is some scientific backing for her fears. There's a theory of co-adaptation that essentially states that each cell is very specific to the trafficking between which nucleus and which mitochondria are actually in the cell. And for the first time, we're disrupting the specificity of this relationship and introducing a completely new parent, either via PNT or MST. Also, we've seen this in lecture 11. There's not much we know about the shuttling between the nucleus and the mitochondria, and we might mess something up. But there's huge benefits for victims of mitochondrial disease. If you're a mother and you have mitochondrial disease and you want to have a kid, and you were previously thinking about whole egg donation or adoption, now you get to have a child that's actually genetically related to you, which is a huge deal. And on top of that, you're actually removing the disease from the maternal family germline because of the very specific way in which people pass down their mitochondrial genome. There are, of course, other options. I just mentioned 2 of them. Whole egg donation has a little more research behind it, and some mothers may side with that just because it's been around for longer. Also, adoption is a great option for people. There's over 17 million orphans in the world right now, and about 250,000 children enter the U.S. Foster care system every year. So you might do a little more good if you do decide to adopt as a parent seeking to have a child. So politically, where are we now? As I mentioned before, in February of 2015, the UK Parliament actually passed let labs move on to the human stage of this. So these clinical trials are going on now, and it's pretty exciting because the regulations were actually put into effect for clinics on October 27, 2015, so this just happened. Furthermore, the US is still discussing some of the ethical implications of this, but we're pausing and we're kind of behind, I guess, the UK again in in vitro fertilization because the FDA is kind of stuck on the safety for the mother and the viability of the children. There's really no guarantees there. And the UK actually made this conversation a little bit more about their citizens having the legal right to pursue these procedures if they so choose. So obviously we've really just talked about the implications for mothers seeking to have children, but it can go much beyond that. It can easily shift towards other genetic diseases. Furthermore, this is a very complex topic, and we want to prevent against maybe having some mitochondrial replacement therapies that are almost designer. And on top of that, what does this mean for the U.S. healthcare system? Is this going to be insured? There are a lot of questions that remain unanswered, and we'd like to answer them before we move on.
Okay, so now for propositions. In addition to the